Omprokash Das, who will speak about minimal model program or Mori program for birational classification of algebraic varieties.
Okay. Thank you very much for the invitation. It's always a pleasure to talk in front of young people. Okay, I'm also young. At least that's what I would like to call myself. Okay, so let's get on with this thing. I'll start. Okay, let's see what is going on. Okay, so I'll start very simply. So everything that we'll talk about here will work over arbitrary algebraically closed field. Okay, so I wrote here, for example, take a complex number, but you can take the algebraic closure of the finite field. Okay, so it will work over positive characteristic as well, almost all of the result. Okay, I'll be more specific where I need to be specific, where some result work only on characteristics. Okay, so let's just start very simply. Okay, with the definition of algebraic varieties, we all know, so just repeat it anyway one more time. That algebraic variety is nothing but a common solution in Kn if K is the field in terms of vector space Kn of multivariable polynomial equations with coefficients in the field K. We'll call a variety projective if it is a common solution of a homogeneous set of homogeneous polynomial equations in some projective space Pn. Okay. Now see, in any geometry, be it algebraic geometry, differential geometry, or any other related remaining geometry, there is always one common goal in geometry, that is to classify all classify all geometric objects. Okay, in differential geometry, you try to classify them different up to diffeomorphism. In topology, perhaps up to homeomorphism. So everywhere you want to classify all geometric objects. Okay, but almost always that is not completely possible. Okay, you will never achieve that goal, that you completely classify them. So what you do is that you weaken your classifying condition. For example, in topology, instead of trying to classify them homomorphically, you try to classify them homotophically. Okay. Similarly here, in algebraic geometry, we would like to classify. Of course, we would like to classify them in the best possible way up to isomorphism. But of course, that is not possible. So you weaken the condition. There are several ways to do this weakening. Okay. So one of the weakening that works remarkably is called birational classification. Okay. So let's define what is called, when do we call two varieties are birational? Okay. So let's say x and y are two varieties. We call that x is birational to y if they have like one open set u in x, one open set v in y. They are both Zariski open sets, so that u is isomorphic to v as quasi-projective or quasi-projective varieties. Then this kind of then we call those two varieties are birational. So basically, I don't expect the varieties x and y to be isomorphic, but they're open. Each of them have open sets which are isomorphic, one open set from each. Of course, non-empty open set. Equivalently, birationality can be expressed in terms of algebra. Okay, so if you take x, y are two varieties, take their function field k, ky. So function fields are, so kx is basically, if you think of x as a affine variety, then go to its coordinate ring A of x, and that's cosine field of that one is the function field. In general, function field the variety is basically a set of all rational functions on x, that's called function field. Okay, so for n, the function field is a quotient of all polynomials of n variable x1, x2, xn. Okay. Okay, so these are two equivalent conditions. Two varieties have isomorphic Zariski open set if and only their function fields are isomorphic as K algebras. Okay. So let's see some examples of birationality. If it is the affine space An, so An has the coordinate, the points looks like A1, A2, An, right? So I can give an isomorphism from An to an open subset of Pn. That open set is, let's say, U0, where U0 is represented that the first component is 1 is to A1 is to A2 up to An. Now see, since first component is 1 in this coordinate system, I can allow A1, A2, An, all of them to be 0 at the same time. That's not a problem. Okay. So therefore, I have in this U0 is literally like very easily isomorphic to An. Okay. So An is always isomorphic to an open subset of Pn, and Pn is the open subset of itself. Or An is open subset of itself, and it is isomorphic to an open subset of Pn. Therefore, An is birational to Pn. Next is, in general, if I take any variety, okay, and just take an non-empty open subset, it is always birational to its non-empty open subset. Obviously, from the definition. None of these things are actually important. First important and interesting result that comes is this. Let's take a variety X, and Z is a subvariety of X. Okay, you take the blow up of X along the subvariety Z. So if you do not know what a blow up is, don't bother at the moment. Okay, it's not going to be particularly important, okay, for the rest of the discussion at all. Okay, but I'm just saying here because that is an interesting example. So if you already know what a blow up is, it will be interesting to see this is that this is actually a birational relation. Otherwise, it's not important really for the rest of the talk. Okay, so if Z is a subvariety, you take a blow up of X along Z, then let's call it X tilde. Then blow up always gives you a birational variety. Okay, birational to the original variety X. Okay. Okay, so that's like a natural surgery process which creates birational variety. Okay. Another like a pictographical example would be this. You take let's say we are in A2, the affine plane, okay, and you take the line y equal to x, the node y square equal to x square into x plus 1, or the cusp y square equal to x cube. Okay. All three of these curves, they're birational to each other. Okay, so seeing them through open sets, like they should have Zariski open set, would be a bit difficult here. Okay. So what you do it instead, you go use the algebraic the condition, okay, that their function field must be isomorphic as K algebras, okay, and that is not so hard to actually see, okay. So for the first, and this is as I said, their function fields are isomorphic to KT. So T is being the variable here, okay, and K is the field, the base field. So you might be thinking why this is isomorphic to KT. See, for the first one, y equal to x, it's very easy to see that it's KT. Okay, you take basically what K of xy quotient by y minus x. So replace y equal to x. So then you have the polynomial ring kx as the coordinate ring of the affine variety, and then this quotient field is the k of round bracket x, which is same as k of t. For the node and the cusp, you need to go to their parametric equation. Okay, so the parametric equation of node is what? It's x equal to t square minus 1 and y equal to t times t square minus 1. And for the cusp, it is x equal to t square, y equal to t cube. Use that parametric equation, you can see that their function fields are exactly kt, isomorphic to kt. Okay, so they're all birational to each other. Okay, so you see that birational varieties could be very different from each other in terms of singularity, right? That the first one line is a smooth, second one is a singular, third one is singular. Okay, so it does sort of like give you kind of counterintuitive that why birationality is a good thing, but we will see later. Okay, soon actually. Okay, see, an easy corollary of the definition of birationality is that if two varieties are birational, the dimension must be equal. Why? Well, dimension can be achieved algebraically as well, right? Remember, two varieties are birational if and only if their function fields are isomorphic as K algebras. Now, if you recall something from Hartstone or any other book, wherever you learned your basic algebra geometry, the dimension of a variety is also same as the transcendental degree of the function field over the base field K. Okay, so well, if they have same function field, therefore the transcendental degree are equal over the base field K. Therefore, the dimensions are same. Okay. So since we know that birational varieties has to be of same dimension, so let's fix a positive integer n and consider a collection of all varieties of dimension n. Because if you consider birational varieties, I know that their dimension has to be fixed. Okay, dimension will be same. So let's fix the dimension first. Okay. Now within this collection C, we're going to define a relation tilde. Okay, we say two variety x and y within C are related by tilde if and only if they're birational to each other. Okay. By the way, let me just clarify one thing. I'm sure it is obvious, but just to be sure, okay, just to be clear, okay. The two varieties of equal dimension are not necessarily birational, of course, right? Think of it as the elliptic curve and the P1, okay? Both of them are curved. Both of them are dimension 1. Of course, they're not isomorphic. P1 has genus 0 and the elliptic curve has genus 1. Okay? So sure, one direction is only birationality implies equal dimension, but equal dimension does not imply birationality. Okay, so that's why you're collecting all varieties of same dimension in the collection C. And then within that collection, define a birational relation x to y. Okay, so yeah, so we say two varieties are related by tilde if and only if they're birational to each other. Okay. Oops. Okay. Now you can actually show that this is an equivalence relation. It's not really hard to see. Okay, x is of course birational itself, and then it is symmetric and it is transitive. Okay, so it's equivalence relation. So of course, when you have equivalence relation on a set, then you can you can have a induced partition, okay, partition by the equivalence classes. So let's pick a variety X from this collection and look at the corresponding equivalence class, the square bracket X. What minimal order program or minimal Mori program, like at a very basic sense, wants to do is this thing, that it aims to find a minimal representative within the equivalence class with good singularities. Okay. See, when you take equivalence class, it has infinitely many elements in the equivalence class, right? So all of them are representative for the class. So I want to choose from each equivalence class a representative that is minimal in an appropriate sense and has good singularities. It may not be smooth, it could be singular, but then has to have a reasonable singularity, not too wild singularity. Okay, so that's what the aim of the minimal order program. Okay. But how to do it? That's a very different question. So now let's start this thing. Let's start with very simple. Okay, we'll start with dimension n equal to 1. Okay, and see how does this classification work. What is the minimal representative? What does it mean to have a good singularity? Okay, so that's what we will do next. Okay, classification in dimension 1. Okay. So let's see the projective curve. Then of course, you can have singularity like the nodal curve or the cuspidal curve. Okay. Okay. So let's do the normalization C tilde of C. Okay. Then we know immediately that, okay, the C tilde is a smooth curve and normalization is always a birational process. Okay. This normalization morphism is always birational. Okay. So that means if I look at the equivalence class of C square bracket, within that class, I already have a smooth curve C tilde. Okay. Not only that, it is a very specific thing about dimension 1 curve that for any two projective curves, the smooth projective curves, if they're birational, they're isomorphic, which means that the C tilde is the unique, the only smooth projective curve within that equivalence class. Okay. For example, that the previous example that I gave you, y equal to x, cusp and node, within those three curves, if you, so they belong to all same equivalence class. Okay. And the y equal to x, that line is the unique member that is actually the smooth. If I projectivize it, of course I have to projectivize it. That's all I find. So it will be projective. Okay. So this is it. The C tilde has a smooth, unique smooth curve, projective curve in the class of C. So we just simply call it, this is the minimal model in this case. I mean, minimal model in the equivalence class of C. Of course, this is a temporary definition. We're going to have a very specific definition of minimal model later. Okay, this is just a temporary definition. Okay? So this is it. For a curve, we are done in dimension 1 in this sense that we want to find a minimal model. Okay, and in this case, this is actually smooth, the C tilde. Okay. So what do we do once we do find a minimal model? Okay. So next job is, once we find a minimal model of something, for example, the C tilde here, we want to know the structure of the C tilde as explicitly as possible. Okay, so just saying the C tilde is a minimal model doesn't give us much, right? So we want to know what are the possibilities for this minimal model. Okay, like really classify this minimal model now. Okay? Now see, if you go to the complex number field C, then you know that every smooth projective curves are correspond to compact Riemann. They're nothing but compact Riemann surfaces. Okay, so consequently, as you know, the compact Riemann surfaces are completely classified by their genus, okay? The number of holes within them. Okay? So the smooth projective curve C tilde that we found in the previous slide, if that one has genus 0, then I know that it's going to be P1 by classification of compact Riemann surfaces. I mean, over complex number. If it is of genus 1, that is elliptic curve. If it is of genus greater than or equal to 2, then for each of these genus 2, genus 3, genus 4, there is a curve called curves of general type. Okay? So this is it. For curve, we know exactly what the minimal models could look like. Okay? Of course, there could be two elliptic curve, more than two elliptic curve, of course there are, which are non-birational to each other, non-isomorphic to each other. So they belong to different equivalence classes. Okay. So what I mean is that, let's say that we are in the second case, the genus of C tilde equal to 1. That does not mean all elliptic curves live in one single equivalence class. That is not. What I mean here is that if say genus of C tilde equal to 1, and then you look at all these kind of equivalence classes, each of those equivalence classes, the minimal model is an elliptic curve. Okay? But they could be non-isomorphic, non-birational elliptic curve. Keep in mind that for smooth projective curves, they are birational if and only if they're isomorphic. Okay, so birationality is same as isomorphic in case of curves. Okay, but the point here is that we know explicitly how they look like, the minimal models. Okay, so these are the two objectives of minimal model program. First, find a suitable minimal model, and then try to classify it as explicitly as possible. Okay? That you want to know exactly what they are. Okay. And moreover, apart from this just genus classification, we also know the modular space of each of these curves due to Delling and Mumford, that MGN and those spaces. So this is it. So basically for curves, we know everything that there is to know in terms of minimal program. The next thing is surface, dimension 2. Now let's go to dimension 2, n equal to 2. Okay. Let's start with the projective surface. Okay. Now, unlike this curved case, if you normalize S, that is not a smooth surface. Okay. Normalization does not give a smooth surface in case of dimension 2. Okay. So what we do is take a resolution of singularity. Because so resolution of singularity is there's a process of taking it by blow up and stuff. I'm not going to that detail, but the point is that it exists. Okay. Residual singularity of surface exists. In fact, residual singularity of any varieties in characteristic 0 of any dimension exists due to Hironaka. And originally for surface, it is Zariski, Abhayankar, Hironaka combined. Okay. Okay. So now, still this residual singularity is by definition is birational to S, original S. Okay. But here's the very bad thing about the resolution of singularity. Okay. See, resolution of singularity is not unique. Okay. This S tilde is a very non-unique. It's a smooth surface, but it's not a unique class in the equivalence class of S. Okay? In fact, if I take any point in S tilde and blow it up further at that point, this again you get a smooth surface, S double tilde. Okay? That is birational to the original surface S. Okay? So that means, in other words, within the equivalence class of S, there are infinitely many smooth surfaces in that equivalence class. Okay, so in this case, like in this sense, like we have like a good singularity, like means smooth, no singularity at all for representative, but there is no unique choice of the representative. Okay, there's no minimal choice of the representative. That is part of the problem. So remember, we want the minimum model to be minimal in some sense and also good singularity. So good singularity part is actually we have it here. We have a smooth, okay, but we do not have the minimality part here. There are infinitely many of. There is no way to choose minimal. Okay, for curves, the minimality part we said okay, it's the unique curve. Therefore, that is the minimal. Okay, there is nothing else to compare it. So what do you do next? Okay, so let me just go. Yeah, so we know that there's an infinitely many choice for this for resolution. Okay, so we have a good representative in terms of singularity, but not minimality. So in the late 1920s, the Italian school of algebraic geometers, they tried to classify surfaces. Okay, so what they realized at that time was that a smooth projective surface contains lots of redundant informations. Okay, and we need to remove these redundancies before we can start classifying them. Around the same time, 1920s and 30s probably, Castelnuovo proved this following very important and useful theorem. Okay, he said that he showed that if you take a smooth projective surface S that contains a -1 curve, okay, a curve is called -1 if it is isomorphic to P1 has self-intersection -1. Okay, so I'm not going to the any detail of what does that mean. Okay, but anyway, if it contains a -1 curve, then that curve could be contracted by morphism f from S to S prime to another projective surface, smooth projective surface S prime. Okay, so that f of C becomes a point in S prime. This is possible. Okay, that you contract the -1 curve, still you get a smooth projective surface. Okay? So you can see that you can repeat this process, right? If there is a -1 curve, contract them. Okay, then repeating this process finally many times, you will eventually you will arrive to a surface. Let's call it S min. Okay. Such that this S min does not contain any -1 curve. Okay? This is what we would like to call a minimal surface. It is actually called a minimal surface, not that I would like to call it. It is called a minimal surface. Okay, it does not contain any -1 curve. Okay, and temporarily again we call this is our minimal model. Okay, although it is not minimal model in a precise sense that we'll see later. Okay? So minimal surface. Okay, okay. So now again, once we have the minimal like candidate for the minimal model, we have good single. S min is a smooth surface, and it does not contain any -1 curve. So this is our choice for each equivalence class. So this is what I'm going to do. Take a starting surface S projective. It could possibly be singular. Go to a resolution singularity S tilde, and from there start doing the Castelnuovo's theorem. Okay, that if S tilde contains a -1 curve, contract it. Okay, so eventually go to a curve that is S min that does not have any -1 curve. That is our candidate now for the good representative. Okay. It's a minimal surface, and it does not, and it's smooth. Okay. The minimal surface, just like the curves, minimal surface is also classified. It can be classified. Okay, it is already done. There are 8 different classes. It's P2, minimal rule surfaces, elliptic surfaces, abelian surfaces, K3 surfaces, Enrico surfaces, Bile surfaces, and surfaces of general type. And the modular space are known for each of these classes, okay, at least over complex numbers. In positive characteristic, at least the subset of general type is still not known, okay, the modular space of that. So, yeah, otherwise we would have very good control over this thing, okay, in dimension 2. So what about the higher dimensions? Okay. So in the higher dimension, we would like to dimension 3 and higher, we would like to do exactly the same thing. Contract the bad curves. By bad curves, I mean something that resembles -1 curve. You see, in dimension starting 3 and higher, the -1 curve does not make much more sense. Okay, so but we'll call those are like those type of curves are bad curves. The curve that needs to be contracted to go to some minimal variety sort of things. So we'd like to do exactly similar things in dimension higher dimensions as well. Okay, contract bad curves and go to a minimal variety. Which we will call a minimal model, and then classify the minimal model as explicitly as possible. Okay. So before I can go say anything about higher dimension, which is the main part of the heart of this talk, I have to actually we have to go through some definitions first. Okay. So let me go quickly over this definition. A normalized X is a normal algebraic variety. A Cartesian divisor is called NEF if the divisor D intersects every curve non-negatively. An example is that if you take P2, it's a curve of degree D is a NEF divisor because it by Bayes' theorem it will intersect every other curve of degree D prime, okay, because all the number of intersection point is D times D prime. Okay. So that's a NEF curve. It is in fact ample more specifically. In general, any ample divisor is NEF. Okay. And finally, if you want something that is an ample but that is NEF but not ample, just take a proper morphism and take a pullback of an ample divisor from the base Y. Okay? So H is ample divisor, f of a star of Y is a NEF divisor which is not ample. Okay? So it's explicitly NEF but not ample divisor, and all NEF divisors are ample H. Okay. Next, let's go to something called canonical sieve. Okay. So you have a variety, projective variety X. Look at the omega 1X, that is the differential 1 form of this thing. Go to its top exterior power. That is a sieve of rank 1. Okay. Actually, here you may need to take a double dual. Okay. I forgot to write that down here. Sorry, there's a typo. Okay. Okay. So anyway, this is called a canonical sieve. Okay. And this corresponds to canonical sieve of rank 1 actually. So it corresponds to a divisor, non-canonical divisor, although non-unit divisor called a canonical divisor. We are going to denote it by Kx. Okay. Now here's the first definition. This is the actual definition of minimal model. Okay. So variety with mild singularities. So I have quote unquote mild singularities. I'm not going to specify what mild singularity means. So it's totally not possible. Okay. But just assume that singularities are good. We have a good control over the singularity. So for now we simply assume there is no singularity, it's just smooth. Okay, no problem. Okay. So variety with mild singularity is called a minimal model if the canonical divisor is NEF, i.e. the Kx dot C is greater than or equal to 0 for all curves C. Okay. Okay. Now, if X is a curve, means okay. If X is a curve, then Kx being NEF is same as what? So if X itself is a curve, then intersecting Kx with the X itself simply means take the degree of the canonical divisor Kx. Okay. So Kx being NEF translates to degree of Kx being non-negative. Okay. So that means in this definition of minimal model, only the elliptic curves and curves of genus greater than or equal to 2 are minimal models because they have degree elliptic curve has degree 0. The curves of genus greater than or equal to 2 has degree 2g minus t. So g greater than or equal to 2 means it's greater than or equal to 2g minus 2 is also greater than or equal to 2. It's positive. Okay. And P1 is not a minimal model in this definition. Okay. Okay. For surfaces, if you take either abelian surface or K3 surface, then Kx is linearly equivalent to 0. Okay. Therefore, it's of course a minimal model. In general, if you take a hypersurface of degree D in Pn, so that the D is strictly bigger than n plus bigger than or equal to n plus 1, then that is actually that HD is actually minimal variety. It's a minimal model, okay, of its own. Okay, because K of HD canonical is actually NF. You can see by this adjunction formula. Next is okay, few more definition. Then we will go to the main part of the minimal model program. Okay. So now the next definition is called something called a Fano variety. Okay. Yes. So if a variety X with mild singularities, again you may assume it is smooth. Okay. It's called a Fano variety if minus of the Kx is ample divisor. Okay. So the anti-canonical divisor is the ample divisor. A simple example is Pn. Okay. If you take the Pn, you know that the canonical sheaf or the canonical divisor for Pn is given by the structure sheaf O of minus n minus 1. Okay, so that if you take the negative of that, so O n plus 1, that is ample, right? So Pn is a Fano variety. Okay, in general, if you take any generic hypersurface HD, so that D is now strictly smaller than n plus 1, then that is a Fano variety. Okay, because of this adjunction theorem again. Next, the last definition, hopefully, no, actually, okay. So yeah, a Mori fiber space. Okay. A Mori fiber space. What is a Mori fiber space? Again, it's a variety X is called a Mori fiber space if there exists a fibration, that means a morphism, a surjective morphism with connected fibers from X to Y, so that the dimension of the base is strictly smaller than the domain, and the fibers now are Fano variety. The variety X itself may not be a Fano variety, but the fibers are Fano varieties. Okay, at least general fibers. And see, of course, a Fano variety is of course a Mori fiber space because the Y is a point in case of Fano variety. Okay, so Fano variety can be thought of as a Mori fiber space, no problem. So one example of Mori fiber space is that take any smooth projective variety and take a EBN vector bundle and take the projective bundle. You know, the projective bundle, the fibers are all Pn, right? Okay, or of n is appropriate of n is going to the rank of E minus 1. Okay, so that's a Mori fiber space. Okay. Okay, so here's the thing. Okay, yes. So in terms of, so you're almost there. Okay. Okay. So in higher dimension, in dimension greater than or equal to 3, one of the main difficulties of finding a minimal model, a minimal representative in each equivalence class, is the lack of a good contraction theorem analogous to Castellano's theorem of surfaces. Okay. See, I can do exactly the same thing. Start with a variety X and take a resolution singularity. It exists at least over complex over characteristic 0 by Hironaka. It's a very famous theorem of Hironaka. So it exists, and then if I had a Castellano type of theorem, then start contracting, remove all the bad curves, and you would have a minimal thing. But that contraction theorem does not exist in higher dimension. That is the problem in starting dimension 3. But see, if you look at the Castellano's theorem, so this obstacle, that not having a analog of contraction, Castellano's theorem in higher dimension, it was a huge problem. Okay? So there was absolutely no progress in the minimal order program or this kind of contraction theorem for 60 years after 1920. Okay, then in 1980s, Mori made the following simple yet very remarkable observation in Castellano's theorem. Okay, that he observed that what Castellano is saying, that you can contract -1 curve. Okay, but a curve C on a smooth projective surface is -1 curve if and only if when I intersect the curve C with the canonical divisor of S, that one is -1. At least in particular, it's a negative number. Okay, so -1, that number was not important for him. The fact was important for him is that it's a negative, that intersection is a negative thing. Okay, so Mori's idea was simply replace the question that is there a -1 curve on S by the question is the canonical divisor Kx nef or not. Okay, see, when there is a -1 curve, because then Ks dot C is -1 in particular is a negative number, so this is definitely not nef. Okay, so ask this question now instead. Is the canonical divisor nef? Okay, sorry, it should have been Ks. Okay, I have it Kx. Okay, so yeah, so that's the next question. Is the canonical divisor nef? So now when you see the first time this question, it is well, yeah, it's a good question, but what if the answer to this question is no, it's not a nef? What do you do next? If it is a nef, then yes, we will call it a minimal model. That's our definition. But if it is not nef, what do you do? It seems like there is absolutely nothing we can do about it. Okay, but that is what is what Mori did, like his main work. Okay, or that he gives a very decisive information in this case. Okay, that what happens if this is actually not nef. Okay, he shows that this is all done in 1980s, 85, 88, around that time. Okay, I think starting from 82 or 83. Okay, that if Kx is not nef, then there exists a contraction of Kx negative curves. What do you mean by Kx negative curves? I mean that the curve that has intersection with Kx negative number, not necessarily -1, absolutely not. You cannot say that in higher dimension. Okay, but a negative number at least. Okay, if you have a curve intersecting negative numbers, you should be able to contract it. And yeah, he shows that there exists a contraction like this. Okay, this is the very big moment of the conception of the higher dimensional minimal order program. Okay? But there are some problems. Okay, this theorem is not enough, as you'll see. See, let's go back to the surface case again for comparison. Okay, in case of surface, we are contracting curves, right? Because for surface, the only thing is surface, then curve, then point. There is nothing in between. Okay, there is like a point and surface, and in between there is a sub-varieties are curves. So whenever you contract from a surface, you are contracting curves. and curves are codimension 1 subvarieties on S. Okay, so the natural generalization of curves in high dimension would be divisors for high dimensional varieties. Okay, when I'm contracting curves in surface, we would contract divisors in high dimensional varieties. Okay, because divisors are codimension exactly 1, okay, in high dimensional varieties. But unfortunately, just contracting divisors in high dimensional variety is not enough to get a minimal model. Okay? So more specifically, there are 2 types of contraction in higher dimensions. Okay? One is exactly, as I said, contract divisors. Okay, so it is called divisorial contraction. You take a variety X and you contract a divisor by morphism F from X to Y. This is called a divisorial contraction. So this type of contractions are good. It means that if what do I mean by good? It means that if X has a good singularity, mild singularity, the Y will also have mild singularity. Okay. And there is another type of contraction called small contraction or flipping contraction. Okay, that instead of contracting divisor, you contract divisor codimension 1. So you contract something of higher codimension, codimension greater than or equal to 2, or dimension less than or equal to n minus 2 from X. Okay, so for example, if you take a 3 fold, you will contract, instead of contracting a surface, let's say you're contracting some curves, finite element curves from X. This would be an example of a small contraction or flipping contraction sort of things. Okay, so you're contracting a subvariety Z, which has codimension at least 2. See, this type of contraction is actually bad, very, very bad. Okay, it's extremely severe contraction. I mean, Y is always singular when you do this kind of contraction, even when X is smooth. Y is like necessarily a singular variety even when X is smooth. Okay, in this contraction. But unfortunately, this type of contraction is unavoidable in the minimal model program. Okay, so we have to deal with it. So I have given lots of definitions. Okay, so now we are ready to actually describe what a minimal model program is. See, when you define something in terms, when you say something that's some program like minimal model program or Langland program, when you say the word program, it automatically means that there is an algorithm for it, for the process. Okay. So that's what next is the minimal algorithm of the minimal model program. Okay. So this is the chart is basically the heart of the minimal program. That's what we intend to do here. Okay. So start with a variety X with mild singularity. Again, for our purpose, let's assume that X is smooth. In fact, okay. Remember what you want to do. Our objective is that look at the equivalence class of X and find a minimal model in the equivalence class that is minimal in some sense and also have good singularity. Okay, possibly not smooth, but at least mild singularities. Okay? So that's what we are doing, starting with the variety X, and whatever we do in this diagram, every step will be living. Every step, the output will live within the equivalence class. Okay, we will not go down to the equivalence class of X. Actually, the originally that we define the equivalence class using the birationality relation. Okay, so start with the X with the mild singularity. Let's say its fact is smooth. Then you ask this question: is Kx NAF? If the answer to your question is yes, then that's it. That's the minimal model. It is smooth. Then we are done. You end the program right there. Okay, it's a minimal model. You go to the right hand side. Okay. If the answer to this question is no, okay, then by Mori's theorem there exists a contraction. Okay, but as I said, there could be 2 types of contraction. Okay, actually there's a third type of contraction that I said it before, saying the divisorial and flipping contraction. Okay, let's just, since I did that, I have to say it differently. Okay, there is a contraction. Okay, so after the contraction, you actually judge this. Okay, look at this thing, whether the base of this contraction Y has a dimension equal to X or strictly smaller than X. See, when you contract things, if it is a birational contraction, then the base will have, the Y will have exactly same dimension as X because it's birational. If it is not a birational contraction, then dimension of Y will be strictly smaller than X. Of course, it cannot be bigger. It can never be bigger than X because you are contracting things. Okay. So if the dimension is strictly smaller than X, then automatically this one becomes a Mori fiber space. Okay. Remember, we defined Mori fiber space before. Mori fiber space means that the fibers of these morphisms are all Fano varieties. That means the anti-canonical divisor of the fibers are ample divisor. Example is you take a projective bundle over any of a vector bundle over any variety. Okay, take a projective vector bundle E over a variety X and take a projective bundle. That's an example of Mori fiber space. Okay, so if the dimension and then so if the dimension of the base contraction Y is smaller than X, then it immediately becomes a Mori fiber space. And this is Mori fiber space is not a minimal model. Okay, but it is in this case it's simply the fact that the equivalence class of X does not have a minimal model. Instead, it has a modifier space, but that is still a positive outcome because modifier space can be classified. Okay, so it's not a bad thing. Okay, so and the other thing is that if there is a modifier space, then there will be modifier space and minimal model. They are like two exclusive cases. If there's a modifier space, then there is no minimal model. Okay? But still, like it's having modifier space is not a bad thing. Okay, so let's say we are in the situation no, the dimension of Y is in fact equal to X. So the no, so then means it is a birational contraction. The base has same dimension as the domain. Now we ask, is it a divisible contraction? It means are we contracting a divisor from X to get a Y? Okay. If it is a divisible contraction, then it's very nice. Okay, then it is yes. Then you simply replace your X by Y and continue this program. Okay, go run through it again. But if it is not a divisible contraction, then it's a contraction that you're contracting something of codimension greater than equal to 2. Okay, it means that you're contracting curve from 3-fold or surface from a 4-fold, dimension less than equal to 2 sub-varieties. Okay, then there is a conjecture. This thing that. I mean, yeah. So then you have this X to Y, but this, as I said, that Y will have a horrible singularity. Okay, it's a extremely bad singularity, so bad that you cannot replace X by Y and run with this program. It will not make sense running with this program. It's not possible. Okay, so you need to replace this X and this Y by something X plus. Okay, and then you replace X by X plus. So this is conjectural whether this X plus this morphism A plus to from X plus to Y is exist or not. This is called flip conjecture. I will come to that thing later. Okay. So if let's say I assume the conjecture, flip conjecture, it does exist. I can find a better variety X plus that is birational to both X and Y and has good singularity. Then replace X by X plus and continue with this program. Okay. So that's it. So this is the minimal model program. You start with a variety, ask whether Kx is NEP. If it is NEP, you have a minimal model. If it is not NEP, then you have a contraction. If the base of the contraction is smaller dimension, that's the modifier space. If it is the same dimension of the domain, then it's either divisible contraction or flipping contraction. If it's a divisible contraction, you simply replace X by Y and continue with the program. If it's a flipping contraction, you do not, then you are not sure if you can go to the next step. Conjecturally, you can, that you should be able to do a next step, replace Y by some other variety, third variety, X plus, which is conjecturally exists and which has good singularity, and then continue the program. Okay. So there are two obvious conjectures related to this minimal model program, this algorithm. Okay. First is the existence of flip. As I said, one of the steps in a minimal model program is conjectural. Okay, so like that's a problem. So the first conjecture is that the flip of a flipping contraction always exists. Means that if you have a flipping contraction X to Y that contracts something codimension greater than equal to 2, then the singularity of Y becomes very bad. Then I want to replace Y by something X plus. Okay, that X plus exists. That is the first conjecture. Next conjecture is see termination of flips. Here's the thing. Anytime you define it using an algorithm, the natural question is, does this algorithm terminate after a finitely many steps? Okay, that's a natural question to ask. Okay, and the point is that we do not know for MMP. That is a big conjecture whether it terminates after finitely many steps. We know in many cases when it do terminate in finitely many steps, but a conjecture is that if the conjecture is called termination conjecture, it should terminate at finite steps. And see, here's the thing, that the only obstacle here is that the flipping part, when you're doing this the smaller flipping contraction. Okay. If you do divisible contraction, I know that we can say that very easily that you can only have finitely many divisible contractions. Why? Because each divisible contraction reduces the Picard number of a variety exactly by 1. And Picard number of a variety is always a positive integer. Picard number of a variety cannot be 0. It's not possible. Okay? Unless it's a point. Okay. So as you start with a variety, you start decreasing Picard number, it will has to stop at least when it arrives 1. It cannot go any below than lower than 1. Okay. And each contraction reduces Picard number by 1. Okay? Exactly by 1. Okay. So that there's no like repetition that it does not change Picard number at all after a stage. It does not happen. Okay. With the divisible contraction. However, flipping contraction does not change Picard number. The flip does not change Picard number. Okay? That X plus that you're replacing, see, this X to Y, it does change Picard number by 1, decrease the Picard number by Y by 1 in Y. But again, when you replace Y by X plus, it puts it back again. Okay, so X plus and X has exactly same Picard number. Okay, so there is no natural invariant to control the the number of flips that you can have. Okay? So this is why it's not known whether in general that the sequence flips will terminate or not. And then there is the final called abundance conjecture. Okay? So saying once you do have a minimal model, that means you have kx equal to nf. This is a question that I got asked many times. I see I have only 5 minutes, so let me be quick. That whether the kx, so what does, if let's say I do have a minimal model kx equal to nf, why is that a good thing, having kx equal to nf? That's a very numerical property, right? So why is that a good thing? So the good thing is that this is the next conjecture, this abundance conjecture. Okay? That once you do have a minimal model, then kx is not, that's not it. If kx is not, kx is actually semi-ample, means you will always have another sort of contraction from x to y, such that the kx is pullback of a divisor from the base. Okay? And each of the fibers of this morphism is a Calabi of varieties. Okay? So this is something very significant. Okay? So what is the current status of this program? Okay. So okay, yeah. So let me tell you. Okay, before I say anything about the conjecture. So this is the upshot of the minimal program. What do you get from the minimal program? The prediction of the minimal program. So minimal program basically gives us this. Minimal program along with this conjecture that I told you, abundance conjecture, flip conjecture, dimension conjecture. If you believe all of this conjecture, then the minimal program says exactly the following thing: that every projective variety X with mild singularity is birational equivalent to one of the 3 classes of variety. Either it's birational to a Mori fiber space X, that means it's birational to X, either X has a fibration X to Y, where fibers are Fano varieties, or it's a birational to a variety X, which is a Calabi of fibration over some other variety Z, or it's birational to a variety of general type. So these are the 3 varieties. In particular, it basically says that if you want to classify all varieties, okay, in the modular sense or in birational sense, you have to only look at 3 classes of varieties. These are the fundamental classes of varieties: Fano varieties, Calabi varieties, and varieties of general type. This is it. This is the precise information that minimal program gives us, along with its conjecture, if you believe the conjectures to be true. Now, what about the conjecture? Are the conjectures true? The conjecture, the first one, the existence of flip, that one was proved in dimension 3 in 1988 by Mori, which led him to his field medal, okay, in the later year. And higher dimension people try to do this as very interesting actually history. So in dimension in 1988 it was proved by Mori, and then people tried to do it for another 20 years, try to prove it for dimension 4, okay, without much success. Then in 2006, Christopher Hagen and James McKernan, okay, this one here, they showed that there's a breakthrough result that year, okay. They proved that flip exists in every dimension, not just dimension 4, all dimensions. Okay, they were able to do induction on everything. They said you do not need to focus on dimension 4. You can do induction on dimension and show that it exists in all dimensions. This is a huge result. Okay, so they proved. So again, all of these things in characteristic 0. So characteristic 0 flip exists. Okay, in all dimensions. But termination conjecture is still not proved. Okay, there are special cases where we know, but not in general. These characteristics 0. So what about other characteristics? In positive characteristics, there was another breakthrough in 2013 again by Christopher Higgins and other authors, Kian Yang Su. They showed their minimal model program, they can prove existence of minimal model program flip and all these things, termination of flip in dimension 3 in characteristic p greater than 5 in positive characteristics. And this was done in a very interesting way using tight closure theory from the commutative algebra, okay, F singularities. This was something very remarkable, very new ideas. And then there are lots of progress. They did basically the fundamental cases in this positive characteristic, and there are lots of other other people contributed to complete the program in dimension 3. And then yeah, so like the abundance conjecture in dimension 3 is also known in characteristic 0 and positive characteristic as well in many cases. People contributed: Birkar, Waldron, myself, Su, Zhang, Wilsek. So let's just 1 minute, I'll tell you this thing that, so minimal program is there for characteristic 0, positive characteristic you only know up to dimension 3. In characteristic 0, we know a lot, okay, but still not the complete thing. And all of those things are projective varieties. But there is a new thing, minimal program for scalar manifolds which are not projective. Okay, so this thing was started in the late 90s by Campana, Peter, Horing. They showed a lot of the cases in dimension 3. And this is the sort of the thing that I'm currently interested in. Okay, I will stop here. Thank you.
Thank you so much for your excellent talk. So I'd like to invite the questions from the participants.
Okay.
So are there questions for the speaker?
Yes, I have a question.
Sure.
How do we know that there are finitely many minus one curves on the, I mean, on the surface that you were talking about? I mean, you said after.
Yes, so there is not -1 finally many -1 curve in general. In fact, there could be infinitely many -1 curve. For example, if you take a P2 blown up at 8 points or more, okay. But the fact is that what is happening is that each time you contract a -1 curve, it reduces the Picard number by 1. And here is other thing, okay. When you contract something, you change the intersection property of the variety, okay. So for example, like I said, if you take a P2 blown up at 8 point, it has infinitely many -1 curve, right? But if you contract one of those -1 curve, you go to, then that becomes a blown up P2 at 7 point. That one has now finally many -1 curve. Why does that happen? Well, because when you contract things or blow up things, you change the intersection property of the variety, okay? So the number of -1 curves heavily depends on the contraction or extraction of curves, okay? So the reason I know that I can, so what I'm claiming there is that there are not finally many -1 curve. I'm claiming that I can contract finally many curves, and after a certain point there are going to be no -1 curve, because yes, this two are obviously related. Yes, this is the reason, okay, that contracting -1 curves actually changes the behavior of the intersection property of the variety. And so what I can tell you that you might be wondering that at least how do I know that I will stop, right? Okay, you will stop for sure contracting -1 curve, because each contraction reduces the Picard number by 1, right? Okay, and a variety of positive dimension must be a positive Picard number, okay. So clearly, if you start contracting -1 curve, each time dropping the Picard number 1, 1, 1, 1, it has to stop at some number, right? You cannot continue, okay. So that one tells you that at some point there will be no -1 curve.
Okay.
Yeah.
There's one more thing. So I think in slide 44 or something, I could see C and D being divisors, and their intersection number was greater than equal to 0. I think it's in.
Sorry. What is the question again? Say it again.
So there were two divisors C and D
Uh-huh.
on a variety X of an arbitrary dimension. I mean, the dimension was not 2.
Uh-huh.
So the C dot D was taken to be greater than equal to 0.
Yeah, so C is not a divisor. C is a curve and D is a divisor.
Oh, okay.
Yeah.
I see.
Okay. D dot C is a divisor, C is a curve.
Yeah, so there's one more thing. So at the end, so I have not really seen, well, the only thing, I mean, I've seen for the surfaces when we contract a -1 curve, there are no introduced singularities, right?
Correct.
But I could hear repeatedly that there are, I mean, when we do it in higher dimensions, it is not the case.
Correct.
So I was wondering if there are like
Examples.
an example of
Correct. Yes. Of course, I couldn't give it here. Here's the example. Okay.
Yeah.
Take a abelian threefold. Okay.
Okay.
And quotient it by Z2, the group. Okay. Group of order 2. Okay. Then you will have, let's say, 2 to the power, let's say, how many 6? 36. You will have 36 singular points. Okay. In that quotient, quotient of A3, the abelian threefold of dimension 3 over complex number, let's say. So there are 36, 36. Yes, 2, okay, just let me just check, okay. 2 times, okay. 2 to the power 6, no, not 36, 2 to the power 6 number of singular points, okay. That one. If you blow up that one, that thing, okay, that one becomes smooth again, okay. If you blow up this 2 to the power 6 number of singular points, okay. And I'm not saying all this thing clearly. I said that there is a contraction, right? Those contractions are very specific type contraction called contraction of extremal ray of the Mori cone. Okay, you can see that if you once you do blow up this 2 to the power 6 number of points of this quotient of abelian threefold by Z2 action. Okay, each of this blow up of this 2 to the power 6 point are extremal rays, and those are the only extremal rays. Okay, negative extremal rays of Kx. Now see. And those are all divisors, right? So if you contract any of those things, you are going to get a singular variety.
Okay.
Does it make sense?
Yeah, it was a little fast. So is there a
Okay.
reference?
Yeah, let me do say it again. Sorry.
Okay.
First, I am aware of that. I've been told it many times. Okay. Let's take an abelian threefold, A3.
Okay.
Quotiented by the group Z2. Z1 to Z. Okay.
Yeah, sure.
then you can calculate that it has 2 to the power 6 number of singular points. This is a singular variety, right?
Okay.
Okay.
Yeah.
And then you blow up all those singular points. You can blow up them up simultaneously because they are disjoint point, okay? Disjoint close points, okay?
Okay.
So then you get one single blow up will give you actually a smooth variety, no problem. Okay? And there in that smooth variety, let's call it x tilde. There you look at the Mori cone. Okay? Mori cone will have exactly 2 to the power 6 number of extremal negative kx negative extremal rays.
Okay.
And what I did not say here in my discussion is that the Mori's theorem that tells you there is a contraction. You do not just contract arbitrary things. You contract the kx negative extremal rays of the Mori cone. That is the only type of contraction that you will do. That means you will contract one of these 2 to the power 6 number of extremal rays from x tilde, right?
Yeah.
See, let's say you contract one of them, okay? That means you get a new variety where you have 2 to the power 6 minus 1 number of singular points. So no matter which extremal ray you contract, you will always end up having a singular 3.
Okay.
Right? Because contraction in this case would be the reverse process of blowing up, blowing down this would be.
Yeah.
Right? Because you can think of this 2 to the power 6 number of point, this blow up process as just doing blow up one by one.
Yeah.
So yeah, so it's contracting one by one.
Yeah.
So that's the example.
Okay. Yeah, that's it.
Okay. Any other questions?
Are there further questions for the speaker?
I have a question.
Sure.
So, what happens if you have curves of, even in the case of a surface, if you have curves of higher intersection numbers, negative intersection. So, for instance, a -2 curve or.
Correct. Yes. Okay. Yeah. Okay. So yeah, of course, I have to leave a lot of things here. Okay. So see, if you have let's say kx dot c equal to -2, right? Okay. So you're saying that whether you can contract that curve or not. Is that the question?
Right. So I know that you can contract it, but you get a singular.
You get a single surface.
Right?
You get a single surface. That is very true. Okay. Yes. That is exactly what happens. Okay. But for the contraction does not come from Custom-Lobos theorem. Okay. So you will get a canonical singularity in this case.
I see, but that's allowed in the minimal model program.
In the minimal model program after Mori, okay, that when you ask this question whether kx is nef or not, okay, in this new series of minimal model program, not the Custom-Lobos way of doing.
I see. So also in the Mori contraction, I mean, what kind of object do you contract? Do you contract a divisor or?
Mori, yeah. So you contract either a divisor or a codimension greater than or equal to 2 subvarieties, or there's a third contraction that I don't know how, when I organized, I wasn't being very careful. These are old slides which I edited. For example, you can have a contraction sort of like for example, this thing, like I said, take a projective bundle, right? Okay. Those contractions can appear, which will give you the modifier space. Okay. So you can have a contraction where you completely drop the dimension from x to y.
Right, but what kind of object are you contracting on X? So, for instance, I mean, for divisorial contraction, you are contracting an actual divisor. Right?
Yes. So in a flipping contraction, you are contracting codimension greater than or equal to subvariety.
Right, but in the first step of contraction that you mentioned, what kind of?
So modifier space contraction is not like you are contracting a divisor. You're like contracting a family of, let's say, a family of curves which covers the open subset of X.
I see.
Or a family of subvarieties which covers open subset of that has to be.
Oh, that gives the fibration.
That gives the fibration, yes. Otherwise, you will not reduce the dimension.
I see. Okay. Yeah, thanks.
Okay. Are there further questions for the speaker?
So, okay. I was wondering, what is all of this was in characteristic 0, right?
No, the algorithm and everything, all of it will work in every characteristic, at least conjecturally. But most of it is done in characteristic 0. Yeah, go ahead. Oh, sorry, I stopped you. What is your question?
No, I thought, can you repeat what is possible in characteristic P?
So more specifically in characteristic P, we do know the existence of flip in dimension 3. Okay. And we know that we do not know termination of flips exactly in characteristic P, but we also know lot of the part of the abundance condition in characteristic 3. But in characteristic 0, we do know the existence in dimension 3 particularly. We know existence of flip, termination flip, abundance condition, all of it. Dimension 3. In higher dimension in characteristic 0, we only know existence of flip, all dimension. We do not know termination of free. We do not know abundance conjecture. Abundance conjecture in characteristic 0 is one of the most important outstanding conjecture there is in biaxial geometry. Okay. It has over literally hundreds of applications of that conjecture.
Okay. Okay.
Awesome. Okay, so
Well,
if there are any further questions, let's thank the speaker.